Okay, in this video, we're going to be doing Calc AB Problem Set 87. The problems and a playlist are in the description below. Let's check out these problems. So number one, we want to evaluate. This is like a crazy looking limit. This is definitely not a limit that you're evaluating using like limit rules. To me, this definitely has to be some sort of Riemann sum. So it's the limit as n approaches infinity of the quantity square root of 3 plus 1 over n plus the square root of 3 plus 2 over n plus the square root of 3 plus 3 over n. So you can see like this counter thing happening. You have like 1 over n, 2 over n, 3 over n. It ends at n over n. That's going to help us figure out a bunch of things. And then all of that times 1 over n. So I want to rewrite this as a summation. It's not really required that you do that. I just think it's a little easier. So it's going to be the limit as n approaches infinity, the sum from k equals 1 to n. Now we just have to figure out what to fill in. So you look at it and it's like there was our counter, right? So that's going to give us a sense of like what function are we plugging into, right? So I think it's pretty clear that we could definitely say we're plugging into the square root of something. But in particular, in our summation, there's always going to be a square root of 3 plus our counter over n. So I'm going to say the square root of 3 plus k over n. So I want to rewrite this so that k kind of like is playing a role, because in the thing that you're looking at, the expanded version, there is no like obvious k going on, or sometimes I call it I. And then my delta x is definitely 1 over n. It's just sitting out here. From the summation or from the limit, I mean, if you look at it, you can definitely write it straight from the limit. You can see delta x is going to be 1 over n. You can then see, now remember, this is kind of a choice because maybe there are multiple ways you could go on this. I'm going to say that my x sub k is the thing being plugged into square root. So it's going to be 3 plus k over n. An alternative is you could say that the function is square root of 3 plus x. I'm saying the function is the square root of x. Either way, we will get the same numerical value when we actually evaluate it, so it's okay. I'm going to go from here. Now that I know x sub k, I have to find x sub 0 and x sub n every time. So x sub 0, just let k equals 0, you get 3 plus 0. And then we find x sub n, let k equal n, you get 3 plus 1, so 4. And as I mentioned, I'm looking at this as if the function is the square root of x. And you just have to get comfortable with these. You look at a bunch of them. I have other videos and like some problems that you can do. Once you get used to these, they're not scary. They're really scary when you don't know what you're doing because they look like the worst limits in the world. But it turns out that this whole thing is just a definite integral. And since we know the fundamental theorem, we can evaluate this using the fundamental theorem. So I'm going to do plus 1 times the reciprocal to find an antiderivative. So 2/3 x to the 3 halves, evaluated from 3 to 4. First you plug in 4, so it's going to be 2/3 the quantity 4 to the 3 halves. And then you plug in 3, so minus 2/3 quantity 3 to the 3 halves. I don't think this is really going to look better. I mean, like you can do something with 4 to the 3 halves, right? That's like 2 cubed, 8. So you could say 16/3, but then that minus 2, 3, it's like, it's not going to look good no matter what you do. So I'm going to just leave this one and head to the next problem. All right, we want to evaluate, it's another one. But at least this one's written, like I prefer them written as summations as opposed to like the written out ones. You see both types though, you got to get used to them. Limit as n approaches infinity, k equals 1 to n, sine of pi over 3 plus 2 pi times k over 3n, or 2 pi over 3n times k is another way to read that, times 2 pi over 3n. So I think this one's a little more explicit. I think that's definitely delta x. So delta x. So it looks like 2 pi over 3n, but you could also think of it as 2 pi over 3 divided by n, which in terms of like, if you were going to draw a picture is maybe a little more useful. Like the distance between where you're starting and stopping is 2 pi over 3, and you're cutting it into n equal parts. You can think of it that way. This is definitely the thing being plugged into a function. So I'm going to say that x sub k is pi over 3 plus 2 pi k over 3n. Now we just said on the last problem, once you get to this step, you automatically find x sub 0 and x sub n. If you plug in 0 for k, you just get pi over 3. If you plug in n, you get pi over 3 plus 2 pi over 3. So pi over 3 plus 2 pi over 3 is just pi. And then the function that we're plugging into, I think this one's a little clearer, is definitely sine. I can't imagine anybody would come up with a different function there. I mean, it's possible. You could look at this and be like, the function is sine of pi over 3 plus x. Like you could do that. That would change x sub k to be just 2 pi k over 3n. I don't know why you would do that. All right, we've got everything we need to turn our summation into a definite integral, so let's do that. So it's the integral from pi over 3 to pi of sine of x dx. Antiderivative of sine is negative cosine. And then we're going from pi over 3 to pi. And then, so we need to do negative cosine of pi minus negative cosine of pi over 3. Cosine of pi is negative 1, so the negative of that is positive 1. Cosine of pi over 3 is 1/2, so negative 1/2 is just plus 1/2, so this is 3/2. These are good problems. They take some practice, as I mentioned on the last one. All right, let's look at one more problem. The differentiable function f of x has tangent line 3x plus y equals 7 at x equals 3, and we want to evaluate the limit as x approaches 3, f of x plus 2 over sine of pi x. First thing for me is this is a tangent line for f of x at x equals 3, which means the tangent line can tell me f of 3 and f prime of 3, so I'm going to figure those out. If I plug 3 into the tangent line, I get 9 plus y equals 7, so y is equal to negative 2. So f of 3 is negative 2. And then the slope of the tangent line, which just moved the 3x to the other side, you get negative 3x plus 7. The slope is negative 3, so f prime is negative 3. I'm probably going to need those because this type of problem is almost always a L'Hopital's problem. So I'm just like immediately upon reading it, I think I'm using L'Hopital's. I got to figure things out. All right, so I need to establish the fact that the limit as x approaches 3 of f of x is equal to f of 3, so that I can like take the limit here. So I'm going to say that f of x is differentiable, which implies continuous. And then because of that, the limit as x approaches 3 of f of x is equal to f of 3, which is equal to negative 2. So now I know the limit as x approaches 3 of f of x. That's really what I just did there. Like I knew f of 3 was negative 2, but did I know that the limit had to be negative 2? I knew that because the function was differentiable, which meant it was continuous. We're good to go. So now I'm just going to establish that, so if I took the limit of the top, I would basically end up with negative 2 plus 2, which is 0. The sine of 3 pi is 0. So I'm getting 0 for the limit of the top and the bottom. This is L'Hopital's. So I'm going to write that down so that I'm allowed to use L'Hopital's. The limit as x approaches 3 of f of x plus 2 equals the limit as x approaches 3 of sine of pi x equals 0. Therefore, by L'Hopital's, the original limit that we were given is going to be equal to the limit as x approaches 3 of the derivative of the top, which is just f prime, over the derivative of the bottom, which is pi because of the chain rule, cosine of pi x. Now I'm going to try to evaluate this by direct substitution. The numerator gives me f prime of 3, which we know is negative 3. The denominator gives me pi times the cosine of 3 pi. Cosine of 3 pi is the same as the cosine of pi, which is negative 1. So this works. So we get f prime of 3 over negative pi. And then our final answer, because we know f prime of 3 is negative 3. At the end here, I got it wrong. I'm going to change that in a different color, unfortunately. Whoop, didn't work. There we go. So let's do equals 3 over pi. So 3 over pi is our final answer. Kind of missed a negative sign there. All right, that's the entire problem set. I hope this was helpful, and good luck.